hello, this is session 25 and last of this course. This will be last session on elliptic functions. It is a short introduction to this subject. So we will speak on elliptic functions and a little bit of elliptic curves. This session will be much less precise than other sections. So I will not provide some proofs of many results. First of all, there is still one property of elliptic function that I would like to prove, which is the following one. Remember, in last session we had constructed this Weierstrass elliptic function associated to a lattice, to a set of periods like this. Okay, we are going to see that such a function is very general, or is kind of universal in some sense. So the main result in this context is the following one. We can call it theorem. Assume you have another elliptic function f of z, another elliptic function with the same lattice of periods. Okay, then there exist two rational functions. There exist a couple of rational functions R1, R2, such that f of z is R1 of p of z plus p prime So every elliptic function can be written with the help of Weierstrass function in the lattice, in the same lattice. Okay, well, the proof goes as follows, essentially. Assume first, the first case, assume that f is even. Assume f is even. So if you have some pole, if you take the fundamental parallelogram, if there is some pole here, a1, well, as some zero, we begin with the zeros. If there is some zero here of the function f, as it is even, there is some zero at the point minus a1. And minus a1 corresponds with a point in the fundamental parallelogram. That would be here, more or less. Okay, so let's say zeros come in couples, and in the same way, poles come also in couples. Okay, so if you have the zeros a1 prime, an prime, you have your zeros, and in the same way you have your bi, b1 prime, bn prime, your poles. You have zeros and poles. Okay, and you could consider in this case, if you consider in this case the following function, k of z. A multiple of p of z minus p of ai, p of z minus p of bi, okay, you can see this function that it is holomorphic. You have removed zeros and poles. Okay, this function is holomorphic, and it is an elliptic function, and it is constant. So the function is a constant. So you can write your function f as a rational function of p. So in this way, more or less is that the idea. You could write f as a rational function of p. So this is the even case. If you are in the odd case, if f is odd, it's quite easy also, because you can, for instance, you can consider f over p prime of z. This is the quotient of two odd functions, so it is an even elliptic function. So it can be written as a rational function of P of Z. So you have this writing here. And in the general case, well, it is well known that every function can be written as a sum of an even and an odd function. So write f as a sum of even and odd function, and you will obtain rational functions R1, R2 to write in this expression. So this is a kind of universal function, universal elliptic function associated to any given lattice. Okay. So it's one of the reasons of one of the reasons to study deeply this particular elliptic function. Okay. So we're going to try to study a little bit the expression before. Remember we have arrived to some expression like this at some moment. Okay, so we have some numbers G2, G3 that are associated to a lattice. In fact, this number G2 we can associate to a lattice. You can call G2 is the number, in fact, 60 times 1 equals 20 times. We have a 3 somewhere, so we have a 60 over there, and there is the number G3 associated to the lattice also, that it was let me recall, 140 is 28 times 5. You remember there was a 28 appearing somewhere and a 5 appearing in the expression of the coefficients C2 and C3 some moment. So you have these numbers here. So you could have these numbers as functions associated to some lattice. It is quite clear that, well, if you multiply your lattice by a constant, let's say you take a similar lattice, so something like this, similar lattice, you take a mu and any non-zero constant, well, it's quite clear from this expression that this is omega to the mu to the minus 4 G2. And G3 is mu to the minus 6 G3. So, well, the study of the lattice, any lattice can be transformed, the study of this function can be transformed in the study of this function associated to a simpler lattice. So we could take some omega equal to 1 over omega, some mu equal to 1 over omega 1, and we could consider the lattice generated by 1 and omega 2 over omega 1. And remember, this number we had called it tau. So we're going to consider the lattice generated by 1 and tau, where tau is, we can assume also that it's a non-real number, of course, with positive imaginary part. So can assume that if not, we change the sign of omega 2 and it's like this. Okay? We can assume we are in this case. So replacing, let's say, it's the denominators here, we have something as n omega 1 plus n omega 2. So replacing omega 1 by 1, omega 2 by tau, we have something like, and so we can consider a couple of functions, G2 and G3. These are functions, holomorphic functions, in fact, defined on the upper half plane. Defined on the upper half plane, these two holomorphic functions. Okay? We want to figure out when, these two such, why can we make these considerations? In fact, a function, when we have a lattice like this, and we have some doubly periodic function. Well, elliptics like this, we identify the opposite sides, we have a torus. Okay, so as I told a couple of sessions ago, a doubly periodic function like this can be interpreted as a function defined, P can be interpreted as a function defined on a torus and with values in the Riemann sphere. Okay, this torus is an example of the Riemann surface that can be written as C quotient by this discrete group of periods. Okay, we can try to ask if all torus are equal or not. So when two such torus are equal. So imagine two such torus are equal. Equal, what does it mean equal? Equal means that they are biholomorphic. When we can find a biholomorphism, imagine you have two different lattices like this, and you have a map between the two different lattices. When there is a biholomorphism between these two lattices. Okay, we have here a projection. There is a natural projection on C over this torus. It's in algebraic geometry, in algebraic topology, is called a universal covering of the torus. Well, essentially the projection will be, if you see here, any point of C, you associate a point and you identify points. You go to the quotient. Okay? So this can be, you have a map here by biholomorphism. You have the quotient map here, and this map F can be lifted. It's a fact that this map F can be lifted. It's quite easy to lift, and if this map F turns out to be biholomorphic, you can lift this map F tilde as a biholomorphism there. And we know how biholomorphism of C are. We know that these are always like this, the holomorphism of C. So this map F takes the class of one point to the class of AZ plus B. Okay, so more or less we have this map must be like this. So if we take now Z plus omega 1, for instance, or plus omega, let's say plus omega. Take omega, any point of the lattice P. Well, Z plus omega is the same, represents the same element than Z, so the image must be the same. But the image here is A Z plus A omega plus B. So if we want these two numbers to represent the same element here, A omega must be an element of P prime. So it is necessary, and in fact sufficient, for two tori like this to be conformally equivalent, to be analytically equivalent, so that there exists some non-zero number A such that AP equal to B prime. Well, in fact, we have an inclusion on one side, but as it is biholomorphism, we have the opposite inclusion. So two lattices represent the same torus only if they are similar. If and only if they are similar. They represent the same torus as, let's say, as what is called a Riemann surface. Okay. So is that one of the reasons to consider only similarities like this? Okay. So we can do a little bit more. We can work a little bit with this function G2 and G3. You work a little bit with this function, you can see, for instance, that how they behave under let's say, under Möbius transformation. But what kind of Möbius transformation are we interested? What kind of Möbius transformation are we interested? First of all, recall that we are interested in Möbius transformation that, in some sense, preserve, let's say, the lattice. And remember that if you have a lattice generated by omega 1 and omega 2, another set of generators would be something as A omega 1 plus B omega 2, C omega 1 plus D omega 2, and the matrix A, B, C, and D must be a matrix of integer numbers having determinant 1 or minus 1, so an invertible matrix of integer numbers. Okay, and well, moreover, we're interested in preserving the upper half plane. We need such transformation that, moreover, preserves the upper half plane. And remember, in the theory of Möbius transformation, we arrived to the conclusion that Möbius transformation, the holomorphism of the upper half plane, are exactly elements of GL2R, so can be represented by real 2x2 matrices having positive determinant. So if we are interested in matrices of integer numbers having determinant 1 or minus 1, and moreover we need the determinant must be positive, we will be interested in the set, what is called the set SL2Z. This is the set of 2x2 matrices, of integer numbers having determinant equal to 1. And we want to see,
why do you want the determinant as well?
yes, the determinant in general to have, in order to have here another set of generators, we need that the determinant, we need that this matrix is invertible. An invertible matrix of integer numbers must have the determinant 1 or minus 1. But if we want even more, that you want to preserve the upper half plane, we need it is positive. So we'll be interested in that. So we are interested in Möbius matrices, in Möbius transformations belonging to this set. In fact, this group is sometimes called the modular group in this context. Which is the behavior of G2 and G3 under the modular group. I mean, an element of the modular group can be written like this. With the variable tau, okay, the element of the modular group preserves the upper half plane. Tau is in upper half plane. So we are interested in the behavior of G2 and G3 under these maps here, under the action of this modular group. And, well, it's easily seen that G2 of T tau is equal to C plus D tau to the 4, and G3 well, this is a simple computation. Try to do this computation at home, and we have to realize that in some moment you have a permutation of the elements of your lattice of periods, but you arrive to this conclusion. Okay, so moreover we have some other interesting functions to consider here that are the following one. For instance, we are going to consider the discriminant function. Discriminant function is the function G2. Okay, due to previous consideration, discriminant function, the behavior of discriminant function under Möbius transformation is C plus D tau to the 12 times, And finally, we're going to consider one very special function that is called J. I wrote it here, the J function. J function is going to be defined, we are going to see which is the interest of this function as G2 under G2 or G3? Sorry, G2. Okay. So, or this function verifies that it is invariant by these transformations. Okay? It is invariant by this transformation, this function J. Okay? Due to previous consideration. We're going to try to figure out a little bit how these functions behave. How this function behave. For instance, sometimes it's useful to note, to remark that these functions are periodic of period 1. These functions, G2, G3, delta, and J, are periodic of period 1. For instance, this means, okay, this is quite easy to figure out from these equations here, in some sense. If these are, let's say, periodic of period 1, it can be written in terms of e 2 pi I tau, a new variable called q. Okay, this q is a variable defined from values q different from 0, so the function in terms of this variable has a power series expansion around the origin. And this power series expansion turned out to be, it can be computed, for instance, in the case of G2, it turns out that the origin is a removable singularity, so it's something that begins by pi 4. These are very long computations, very long computations. I will give now a reference, but some terms q times q, etc. G3 is also removable, so it's pi 6 times delta. Is removable also and has value 0 at 0, so it begins by pi 12. Something like this, it's very complicated numbers. And finally, G tau has a order 1 pole at the origin. This is a magic number that appears here, that is I think it is the third power of 12. Okay, if you have read about Ramanujan's life sometimes, so you have seen the film on the life of Ramanujan, there is a curious history about a close number to this one. Sometimes Hardy tells him that he has come in a taxi with the number 1729. That Hardy said, no, it's not an interesting number. And Ramanujan, that was very ill at that moment, told him that it was a very interesting number because it's the smallest number that could be written in two different ways are the sum of two third powers. So one power, you could write like this, and there is another way that I don't remember now of writing this number as some similar sum. And apparently is the it's the smallest number with this property. Okay, but this has few to do with. So it has a pole here of. You can, well, there are many places you can find the details of this computation. One of the book is there is a book of Jones and Singerman. complex analysis, as is quite geometric sometimes, and okay, it's good ideas. It's not the classical book, the most Jones, not the most classical book on complex analysis, but it's quite interesting. And there is also a book of Segal called 8 lectures on complex analysis, something like this, where one of the lectures is about elliptic functions, and it treats this topic quite deeply. Okay, in the notes, when I finish writing, I will finish in shortly, there will be precise references of these books. Okay, in order you could see these computations. Okay, and let us continue. So this function J is invariant by the action of a modular group. Okay, so J takes the same value at T such at any other the point T of tau such at T of tau, where T is an element, any element of the modular group. Okay, J takes the same value. So we could try to figure out what is called a fundamental domain for the modular group. What is a fundamental domain? Normally, when we have a discrete group of Möbius transformation like this, we call a fundamental domain, let's say, some domain in C, let's say U, such that you imagine you have a group of transformations. So a fundamental domain would be some open set U, such that the whole plane set C, or the whole, perhaps not all the complex plane, but some, perhaps the upper half plane or something like this, where it must be defined, the whole set C can be written as the union of T of U, where T is an element of the group. So moving the elements, you cover, you tile all your domain or your plane, for instance, and two of these sets don't overlap. Well, you could impose that they don't overlap, or they overlap only in the borders. For instance, U, TQ have not interior points. Okay, overlap only in the border. It's only points on the border. So the interiors don't overlap. Okay, if T is different from the identity, of course. Okay, and this such set is called a fundamental domain. For instance, if you take the group generated by translations Z plus N, where N is a natural number or an integer number, let's say, so translation like this, fundamental domain would be, for instance, a strip of width 1. This is the fundamental domain. In the fundamental domain, you can see essentially for functions that are preserved by elements of your group, you can see everything. So a fundamental domain for the modular group turns out to be this set, the following set. It is a quite tricky proof that I'm not going to do, but for modular group, as I told at the beginning of this session, I will be much less precise. In this session, I will leave only some ideas. So the fundamental domain is the following set. Take the half circle of radius 1 here. Take the points minus 1 over 2, 1 over 2. And I take some color chalk. So this is a fundamental domain for the modular group. So you can see that no two different elements of this red set are not one cannot be the image of the other for one modular transformation like this, and if you take any element of C, it can be taken by some, in fact by only one element of the modular group, it can be taken into one element here. Well, this is not so difficult. For instance, using translations, you can take any element to element of this strip here, but perhaps it's inside, and you have to use some inversions, things like this, to move the element to your red set there. Okay, so G can be considered as a function defined here, called this fundamental domain called F. G can be considered as a function defined here, okay? And, well, you can study using these properties here. You can, for instance, show that some, let's say, you can figure out some of the values of your functions, G2, G3, delta, and D over this domain. Mainly we're interested in the values of J. For instance, an interesting property is that if two times the real part of some number is an integer number, then G of this number, tau, this number, to call it tau, is real. Okay, so the function G has real values here on the vertical, on these vertical strips, because you are in points with the real part, where the real part is 1 over 2 or minus 1 over 2. So they have real values there. Also, another property is that if Z is equal to 1, then G of Z is equal to its conjugate, so G of Z is real. So also, again, over this part here, it takes real values. Okay, it takes real values. And in fact, it can be shown that, let me verify, that at this point, call it rho, J of rho, the value is 0, and at the point I, here, J of I is 1. Okay, can be verified that. Now, using this representation here, this series expansion around the origin in terms of Q, note that when Q approaches 0, J goes to infinity. And seeing the value of Q, the value Q is 1 over 2 pi I tau, this can be translated in the fact that when we approaches infinity, let's say, this direction, J approaches infinity. J goes to infinity when you go to infinity vertically, in this sense. Okay, when the imaginary part of this number tends to infinity. Okay, so we have here the value 0, the value of J, the value 1 here, real values here, and here the function goes to plus infinity. Okay, and well, at least the modulus of J goes to infinity, and so we have 0, 1 here. No, here it goes. Can be seen that it goes to minus infinity, and here it can be seen that it goes to plus infinity. Okay, so it goes to minus infinity over this line, and to plus infinity of this line. So J transforms the border of F. In fact, the border of F goes to R and goes to infinity and minus infinity in both senses. And moreover, you take any value of C, complex. Imagine C is not real. we're going to see that there exists some value that j takes the value c at some point. In fact, j takes the value c at only one point. How can you do that? Okay, as j tends to infinity, when you go to infinity, well, up to some height, the value c cannot be taken. Okay, you are greater than this, the value of j up to some height is greater than the modulo of c, so it cannot be taken. So you can cut at some point here, and you can take this path. Imagine you take this path. And in order to see if the value j, if the value c is taken in this path, using arguments that we have already used previously, we know that we could consider the following integral. We could consider the integral of along this path of this function. Okay, this integral would give us the number of times the value c is taken on this inside this domain. Okay, if you study closely, more closely this integral, you notice that the integral on the vertical side are going to cancel because of the fact that j is a periodic of periodic 1. And also, the integral here and here is going to cancel using some other properties that j verifies over the points of modulus 1. So, the only integral you have to study, in fact, is the integral along this segment. The function j has the same value here and here. Okay, so this integral, in fact, can be also interpreted as an index, the same way we did before in the proof of one of the Lewis theorem. So it's going to be an integer number, this integral, of course, because the path here is going to be interpreted as a closed path, in some sense, and making the change of variables tau equal to, if we make this change of variables in this integral, you could apply residual theorem. So after making some computations using the expressions of j before, there are some computations to be made, you could figure out that this integral is going to be exactly 1. This is not so easy. There are many computations to be done. But anyway, you arrive to this result. This integral is always equal to 1. So j takes every complex value exactly once. The same can be seen for real, we took non-real values. The same can be seen for real values. We know here that, let's say, all real values are taken because of the connexity of this path, etc. But perhaps we don't know that this function is, let's say, monotonic, increasing, something like this. This function j defined here, but well, it's going to be the case. We have to work a little bit. You take some, imagine that a point would be taken twice, but you change a little bit your path, something like this, and well, you can use the same arguments as before to figure out that each value is taken only once. Okay, so j takes on this fundamental domain every complex value exactly once. And one consequence that could be obtained from this result is the following fact. So we have defined our function g from, we are started from an elliptic function. Elliptic function has two numbers associated, g2 and g3 associated to the differential equation. And well, from these numbers, let's say from lattice, we have defined these numbers and we have defined such a function. So now we could ask so from, let's say, from our lattice, we have defined these two numbers, g2 and g3. So you could ask the converse fact. Assume you have two numbers, G2 and G3. Assume you have these two numbers. Having the property as so does there exist a lattice? Does there exist a lattice such that the elliptic function associated to this lattice has these two numbers? So the differential equation associated is going to be this one. Okay, does there exist? Okay, the answer is yes. The answer is yes. Why? From here you could consider this number, G2 to the 3. Consider this number, and you could call C this number, and you could find, using the previous result, that there exists a tau such G of tau is equal to this number. And well, working a little bit, it's not completely evident, but it is the key fact to show that finally this exists. So this classify, in fact, you have like this all elliptic functions, so all numbers G2 and G3. In fact, this function J classifies all these functions in the all these lattices in the following set. Two such lattices are the same, let's say are analytically equivalent, so by holomorphic, if and only if for a tau associated to the lattice, J of tau is equal to J of tau prime. So if you take a tau associated to one lattice and a tau associated to another lattice, taking two generators such that the quotient is a complex number of positive imaginary part, the function J allows to decide if the two lattices are equivalent or not. And this has a strong connection with the theory of curves. The theory mainly of plane curves, of cubic plane curves. So I will give only a rough idea of these connections. Consider a plane curve of degree 3, a projective plane curve of degree 3 without singular points, only with regular points, okay, over the complex. Well, this has a much, let's say, complicated equation. So you could like to do as you are used to do, for instance, with conics. You take some good coordinates, good projective coordinates to figure out how conics are. And for instance, you know that every conic over the real plane has a modular affine change of coordinates that has a very simple equation. Okay, so you could move also your projective coordinates. And what is the usual way to do that? If you have your cubic curve, these cubic curves have also what is called inflection points, flex points. A flex point is a point where the tangent touches the curve with order at least 3. Any such projective plane cubic plane curve has always some inflection, some flex point. This is a fact that can be studied in algebraic geometry. So you take one of these flex points and you send it to infinity. You send it, if you take projective coordinates x, y, and z, where z equal to 0 is the line at infinity. And you take this point to infinity, to the point 0, 1, 0. Okay? And you take coordinates in such a way that this line here is the line at infinity. So the line at infinity only cuts your cubic in this point. As it is a cubic, as is the order of contact, it has at least 3, and it's a cubic, it cannot be more by Bézout theorem, for instance. Okay? As I told you before, this would be better understood if you have some background on algebraic geometry, and if not, you can run to your closest library to find a good book on algebraic geometry. Okay, on plain algebraic geometry at least. Okay, you can take coordinates like this, and you can take also coordinates assuming that at least the point 0, 0, 1 belongs to the curve. Belongs to your curve, and moreover than over this point, the tangent at this point is the straight line x equal to 0. Well, making these arrangements and making some small computations, you can arrive to the fact that any such projective curve, projective cubic, has an equation like this. Where lambda is a complex number different from 0 and 1. In fact, it's the only projective invariant of the curve. If you go down to Earth, so you are on the projective plane with infinity and heaven and everything, and you forget the heaven and you come down to Earth, you have your equation like this. And this equation reminds you a lot, surely, the differential equation defined by verified by the Weierstrass P function. Okay, so in fact, lambda modulus some small transformations. For instance, you can change lambda by 1 over lambda, or by lambda plus 1, or something like this. So modulus some small transformation is the only projective invariant that one cubic non-singular projective curve may have. And so the projective classification of cubic curves is done like this. So no, this cubic curve is also a Riemann surface. It turns out that this is a torus that we already know because perhaps we could parameterize. So using the previous result, we can show that we can find some lattice, some appropriate lattice. Well, we must do some changes of coordinates, because this is not exactly the equation we had before. You remember that in the equation, the differential equation for the Weierstrass P function, we didn't have the term on x squared in the polynomial that appear, but this term can always be removed by from some equation here doing some linear transformation. It's the same thing you do always when you try to solve degree 2 polynomial. It's essentially what you do. Remove this term to complete the square. You can always remove this term. So this is not a real problem. So using the fact that the J is surjective, you can associate to this polynomial the numbers G2, G3, etc. You find them J and you find some lattice such that this curve corresponds to that lattice. So in fact, that this is a torus, such an algebraic curve is a torus, and in fact, you can prove that the analytic classification of those torus is exactly the projective classification. So two such torus, two such elliptic curves are analytically equivalent, let's say, holomorphic if and only if they are projectively equivalent. Of course, this needs a lot of things to be completed. This is a vague idea. So, in fact, this theory is quite beautiful because it makes strong relationships about different fields. For instance, you have for one part cubic curves. You have for another part, let's say, analytic tori. Let's say Riemann surfaces that are homomorphically equal to tori. You have elliptic functions that are defined in a different way, and there are very close relationships among all these concepts here. And it's only, well, I only wanted to give a rough idea. Elliptic curves can be used for many different things. For instance, can be used for constructing explicitly a universal covering of the plane minus 2 points. and to see that the universal covering of the complex plane minus 2 points is the open disk D. So there is a map that covers, in the sense of algebraic topology, this set, and for this fact could be used, for instance, to provide a proof of Picard's theorem that says that any entire function which avoids two values is constant, because a function which avoids two values, it's a function from here to C minus 2 points. This can be covered by a disk, and such a covering means, using very well known algebraic topology tools, that this function can be lifted here, can be lifted as a holomorphic function. So a lift here, you have a holomorphic function having as image, an entire function having as image a disk, so it's bounded holomorphic function, so it is constant. So, there are several ways of constructing this lifting here. One way that avoids all this stuff, you can construct directly using conformal mappings, etc. That you can read this approach in many books. Let's say the Conway, I guess, or the book of also of Rudin of real and complex analysis. Many books trace this, but this can be also constructed using elliptic functions, for instance. Well, this is a beautiful proof of the fact that of this Picard's theorem. That, of course, Picard theorem can be proven without using all that. There is a completely analytic proof of Picard's theorem that only makes a lot of computations on a lot of estimates on the, let's say, on some sizes. So essentially, it moves to prove that function like this must have always, in the image there, must contain a disk of a certain fixed size, and after that this size, you enlarge this, and you see that it's not possible because it would cover some of the points here. Something like this is more or less the idea. There's a simple analytic proof of that. Okay? But if not, okay, this was very vague, but anyway, it was the last session of the course, so I stop here and thank you for your attention.